Have you ever wondered how Google just knows that two news articles are pretty much the same, even if some of the words are different? Or how a university can scan millions of student essays for plagiarism almost instantly? Well, the answer is this beautifully clever algorithm that basically solved one of the internet's biggest headaches. Okay, let's dive in. To really get a feel for the challenge, let's start with a number. This right here is a pretty conservative guess of how many pages are on the indexed web. Yeah, 4.5 billion. Now, just imagine for a second that it's your job to find all the duplicates and the near duplicates in that gigantic, constantly growing library. I mean, where would you even start? Right. That is the million-dollar question, or I guess the billion-document question. How do you find every pair of documents that are, let's say, 80% similar or more, and do it efficiently without, completely melting your servers? It's just a problem on an unimaginable scale. So let's talk about that for a second. We'll call it the billion-document problem, and we're going to see exactly why the most obvious, straightforward approach is a total non-starter. Okay, so the simple, what we call naive solution is exactly what you'd think of first. You take document number 1, compare it to every single other document. Then you take document number 2, compare it to all the rest, and so on and so on. It's super thorough, for sure, but it has one absolutely catastrophic flaw. And the scale of that flaw is just, well, it's staggering. To compare a relatively tiny set of just 1 million documents, you'd have to do 500 billion comparisons. That number on your screen, that's a 5 with 11 zeros after it. Just massive. And to put that in perspective, a regular home computer running 24/7 would take about 5 full days to finish that job. And remember, that's just for 1 million documents. For the whole internet, forget about it. It is computationally impossible. So yeah, we need a much, much smarter way to do this. And here's the game plan. Instead of using brute force, we're going to use a clever 3-stage pipeline. First, we have to shrink each document down into a small signature. We'll talk about how. It involves a couple of tricks. Second, we run those signatures through an algorithm called Locality-Sensitive Hashing, or LSH. And finally, the LSH spits out a much smaller, manageable list of candidate pairs that are likely to be similar. Then, and only then, do we do a proper comparison. All right, let's dive into that first step, creating these digital fingerprints. Before we can even do that, we have to break each document down into a bunch of unique, overlapping chunks of words. It's a process called shingling. But once we have that, the real magic that creates the fingerprint is a technique called MinHashing. So the core idea of MinHashing is to take that huge, messy collection of text chunks from a document and boil it down into a short, clean signature of a fixed size, like maybe just 100 numbers long. It does this in a really clever way that preserves something called Jaccard's similarity, which is just a fancy term for a score from 0 to 1 that tells you how much two documents overlap. And here is where it all clicks. This is the magic part. The way these fingerprints are built is super special. If you compare two of these tiny fingerprints, their similarity is an incredibly good statistical estimate of the similarity of the original full-length documents. So the bottom line is, we can now compare these tiny little signatures instead of the giant documents. That alone is a massive, massive speed-up. But even with these small signatures, comparing every single one to every other one is still way too slow. And this brings us to the absolute heart of our explainer, the hashing shortcut itself, locality-sensitive hashing. Okay, so you know how with normal hashing, you try really hard to avoid two different things ending up with the same hash value? They're called collisions, and they're usually bad. Well, LSH flips that on its head. It's actually designed to make similar items collide, to put them in the same bucket, while making sure dissimilar items end up in different buckets. So how does it do that? Well, it uses this simple but really powerful trick called the banding technique. First, we take each of our long signatures and chop it up into a bunch of smaller sections. We call these bands. Then we hash each of those little bands individually. Now, if any two documents have even one band that is absolutely identical, they get hashed to the same bucket, and bam, they become a candidate pair that we'll check later. But this, of course, introduces a classic trade-off. If we make it really easy for two signatures to match, like say they only need one tiny band to be identical, we'll cast a super wide net. We'll catch all the real duplicates, but we'll also get a ton of junk or false positives. On the other hand, if we make it too hard to match, we'll avoid the junk, but we'll miss a lot of genuine near duplicates. Those are false negatives. So, how do you find that perfect sweet spot?
Well, the answer to that question is where LSH goes from just being clever to being truly brilliant. It's all about how you tune the machine to create a statistical phenomenon called the S-curve.
Okay, let's just walk through a quick example to see how this works. Let's say we have two documents that are 80% similar. Thanks to MinHashing, their signatures are also going to be about 80% similar. Now, we'll set up our LSH machine with 20 bands, and each band will have 5 rows. So what are the odds that they end up as a candidate pair?
Well, the probability that our two signatures match perfectly in any one specific band is that similarity, 0.8, raised to the power of the number of rows in the band, which is 5. And that comes out to just under 33%. Not great, right? You'd actually miss this pair 2/3 of the time if you only had one band to check. But, and this is the whole key to the thing, we don't have one band, we have 20 bands. We have 20 shots at getting a match. The probability that they match in at least one of those 20 bands skyrockets to 99.965%. It's basically a certainty. We just took a pretty weak signal and amplified it into something we absolutely cannot miss. And this is what's called the S-curve effect. By carefully choosing the number of bands and rows, you create this incredibly sharp dividing line. Pairs that are highly similar, like our 80% example, are almost guaranteed to become candidates. But pairs with low similarity, say 30%, have their already low chance of matching get crushed down to almost 0. It's a probabilistic filter that is just stunningly effective. And, hey, you do not have to take my word for it. We've put a link on this slide to an interactive tool. You can go there and play around with the numbers for bands and rows yourself and literally watch how the S-curve changes. It is honestly the best way to get a real gut feeling for how this works. Okay, so we've gotten pretty deep into the mechanics, but why does this one algorithm matter so much in our day-to-day lives? Let's bring this all the way from theory right back to your screen. The truth is, LSH and different versions of it are running silently behind the scenes all over the internet. It's the engine that powers plagiarism detection software. It helps search engines get rid of duplicate results. It's what recommends products that are similar to things you've already looked at. And it's how news sites can group together the same story from a dozen different sources. It really is a foundational piece of our modern data world. So to recap the whole toolkit we just explored, we start with shingling to break documents down into sets of text chunks. Then MinHashing works its magic to turn those huge sets into small representative signatures. And finally, locality-sensitive hashing uses that awesome banding technique to find the likely candidate pairs from those signatures. It is just a beautiful, elegant 3-part solution. And all this leaves us with one last really fascinating thought. LSH works because it trades absolute 100% certainty for overwhelming probability. It doesn't find the perfect answer. It finds an excellent answer, and it does it incredibly fast. It just makes you wonder, what other problems that seem totally impossible today are just sitting there, waiting for a similar clever probabilistic shortcut?